Hello everyone, welcome back to another class of the fundamentals of particle and fluid solid processing. Today we will be seeing a new section that deals with the flow of fluid through granular and packed bed of particles. So here in this section we will be seeing some important concept. We will be revisiting some of the concept that you already know. So again this section will also serve a purpose of having familiarity with the already known concept and refreshing your memory. The reason that is these things are required in this course is that there are several phenomena happens in the chemical process industry, petroleum industry and other places as well, where there are flows through such bed of, let's say, the catalyst particles. Sometimes it is powdery material. Through the fluid flows through a cake of fine particles. For example, there are fixed bed catalytic reactors, okay, where solid catalyst act as their one of the main component through which some gaseous phases flow or liquid phases flow. Now the point is that in such cases, to design such operations effectively and efficiently, one of the main parameter that we need to understand is the pressure drop across the bed, because there will be the resistance to the flow due to the presence of the solid particles. Now, as I said, the solid particles can be of a bigger size, or let's say the fine particles. Essentially, we have to, our goal in this section is to understand how we measure the pressure drop across the bed, because that is one of the vital component for designing equipment that handles such operations. Okay. So the examples, one of the examples that I gave was a fixed bed catalytic reactor, let's say, where SO2 is converted to SO3 in presence of solid catalyst bed. There can be the drying column that consists of molecular sieves through which the fluid is flowing. Okay. When there is gas absorption into liquid, where the liquid flow is happening from top to bottom and the gas phase is blown from the bottom to the top. So this absorption depends on the surface area available. Okay. Now this pressure drop estimation helps us to give an idea that how much is this available external surface on which this several, let's say, in case of solid catalyst, there the reaction can happen on the solid surfaces, the adsorption can happen, and this solid surface basically dictates that how much resistance will be there as well, the available surface area. So in determining the size of the equipment or designing of this equipment, the expression for pressure drop is very essential. Now the point is that in several in most of the industries, this flow through this such packed beds or the granular beds, or let's say the powders, is not of a single phase flows. Okay. There are multi-phase flows happens in those cases, but for the time being we will focus at first at the single phase flow when it happens through such a bed of the material of several different object of different size that can be of different densities. Okay. So the essential goal in this section is to understand that how the pressure drop will vary when a fluid flows through a stack of particles or a bed of particles, a bed of powders, particles having different sizes, particles of different shapes and similar things. So the point here is that in 1856 Darcy initially proposed an expression when he did the experiment of a fluid flowing through a bed of sand, the water flowing through a bed of sand. Observe that the pressure gradient is basically proportional to the velocity of the fluid, which means the pressure gradient here is the del P by H is proportional to the liquid velocity, where u we define as the superficial velocity that is happening through the bed. Okay, so why the negative sign? You already know this thing, that here the flow is happening from high pressure region to the low pressure region. Okay, so the point here, this frictional pressure drop across the bed having a height or depth, whatever you say, if that is h, then this del P by H is basically proportional to the superficial velocity, where the superficial velocity is nothing but the fluid volumetric flow rate per unit cross section of the bed. So if you have a Q unit of volumetric flow rate happening through a cross sectional area of A unit square, and Q is your volumetric flow rate, that is unit cube per minute, hour or time, then Q by A is basically the superficial velocity. Okay. Now the thing is that this stack of materials or the bed of powder object, whatever you say, when it is packed, if it is not sequentially packed, okay, we call this is that would be a random packing. That you, let's say you take a beaker, you put some sand inside. Okay, now the sand will fill some portion some height of this beaker. Okay, but there will be some void spaces. Okay, so if you pour some water, that water can be soaked in that void spaces or the empty spaces in between the sand particles. Now that space we call as the void space or the voidage. Okay, so the point is, when we talk about such bed of particles, then to understand the pressure drop across such bed, okay, initially let us start with the pressure drop of laminar flow through a tube. We already know that expression, the derivation part we will not go into details, because this is the part where the prerequisite fluid mechanics knowledge will come into play. So this Hagen-Poiseuille equation for laminar flow through a tube has such expression that you can remember or recollect these expressions, where d is the tube diameter or the pipe diameter and mu is the fluid viscosity. Rest other parameter we have already defined, that this is the pressure gradient per unit length or per unit depth of the bed, u is the superficial velocity. The point here is that the packed bed, okay, or a stack of particles of a certain height of this h again can be thought of if, let's say, somehow you have managed to fill the beaker with known size spherical particles in a sequential manner, then it is possible to imagine that the void spaces in between the particles are of this kind of a tube shape void space. Okay, so which means the void spaces inside the packed bed or the stack of the material can be thought of these several tubes that are there inside the bed, through which the flow can happen. And if that imagination you can do, and you can think of an equivalent diameter dE with the equivalent height he, that carrying a fluid that is of velocity ui. Okay, this ui we say the local velocity or the interstitial velocity, interstices in between the particles, okay, or the local velocity. Okay, then the similar expression we can write for this packed bed as well, that is minus del p by he, which is the equivalent height, okay, considering those many of tubes that are there, the superficial velocity of the interstitial velocity, that is ui, and the equivalent diameter de, where k is a constant, okay, that depends on the shape of this tube's path, because the tube's path are basically not straight. Okay, so the point is that it will have tortuous path in reality, through which the water or any fluid can flow when there is a stack of particle. Okay, so this interstitial velocity is nothing but it is the superficial velocity divided by the voidage or the void fraction that is available for the flow. This voidage, again let me define that, it is the empty space in the bed divided by the total volume of the bed. It is a dimensionless number. It quantifies that how much available space is there for the flow. Okay, so this, when we divide the superficial velocity with this value, then we can have the interstitial or the local velocities. Quite naturally, this local velocity is always higher than the superficial velocity. Okay, so the superficial velocity is something like that what you pour in that beaker. Okay, that comes from the volumetric flow rate divided by the cross sectional area of the beaker, and then the water, when it flows inside those sand particles, those velocity if you can measure, okay, that is the local velocity or the interstitial velocity, and that is the superficial velocity divided by that voidage or the void space that is quantified by this epsilon value. Okay, so the relation between interstitial velocity and the superficial velocity should be clear. Now, as I said, this tortuous path in the bed, okay, or through the interstices where the flow is happening, can be thought of as a proportional value to the bed depth. As the bed depth or the height increases, this tortuous path naturally increases. So, this equivalent height is basically a factor of the total height, okay, and that proportionality constant is here k2, where the h is the total bed height. The equivalent diameter or the hydraulic diameter, how do we define? It is 4 multiplied by the flow area divided by the weighted perimeter. So, weighted cross section by the weighted perimeter. Okay. Now, here if you have understood the concept of voidage, now that voidage is through which the flow is happening. So, if A is the total cross sectional area, actual cross sectional area, the area available for flow is basically epsilon multiplied by A, because other portions are filled by the solid particles. So, this flow area is then epsilon A. The weighted perimeter, okay, is in the S superscript subscript B. This B would come at the bottom due to something here that is not showing properly, but it is actually S B at the superscript like it is written here. So, if that is the surface area per unit volume of the bed, okay, then the weighted perimeter is basically that multiplied by the cross sectional area. Again, SB if we define that the particle surface area per unit volume of the bed. Okay. So, this is the this quantity, if we define quantity as a particle surface area per unit volume of the bed, then the weighted perimeter would be this particle surface area per unit volume of the bed multiplied by the cross sectional area. That is what the water or fluid can weight, that much area of the particle, of the particles. Okay. So, the total particle surface area in the bed, then this area, okay, this quantity multiplied by this H, okay, that is the depth or the height of the bed. So, now in other way you can think of this for a pipe. The weighted perimeter is the weighted surface by the length, which is pi dl by L. Okay. For packed bed, the weighted perimeter analogous to that, okay, will be of SBAH divided by the length of the packed bed, and that gives that SB multiplied by the A value. So, this would be our weighted perimeter. Now, if we define another quantity, is that surface area per unit volume of the particles. Okay. So, surface area per unit volume of the particles SV, then SV multiplied by 1 minus epsilon. 1 minus epsilon is basically the solid quantity, multiplied by the surface area per unit volume of the particles is basically the surface of the particles per unit volume of the bed. So, in a more simplified manner, if you follow this expression, that surface of particles by the volume of particles, which is basically the SV, surface area of particles per unit volume of the particle, multiplied by volume of particle per unit volume of the bed, which is nothing but 1 minus epsilon, because epsilon is volume of empty space divided by volume of bed. So, 1 minus epsilon is the volume of particle divided by the volume of bed, and that eventually is this denominator goes out. So, it becomes surface of particles per unit volume of the bed, which is nothing but SB that we defined earlier. Okay. The reason we are doing this is to calculate the equivalent diameter, okay, or the hydraulic diameter. Now, the hydraulic diameter, again we go back to that expression, previous expression, that is 4 multiplied by the weighted cross section divided by the weighted perimeter. So, 4 multiplied by the weighted cross section is epsilon A multiplied by A, epsilon multiplied by A divided by this SBA, where SB is nothing but SV multiplied by 1 minus epsilon. The reason we have converted the SB to SV, because SV is the particle property now. For any particle property, any type of particular shape, you can find out what is the SV value. Okay. So, for spherical object, this SV is what? SV is nothing but 6 by x, or the diameter of the spherical object. It is the surface area of the particle, that is the pi d square, okay, and the pi d cube by 6 at the denominator. that is the volume of the particle. So that is why we have converted that, because we are finding out a generic expression, okay, irrespective of whatever the particle shape is, so that we can understand how much will be the pressure drop across that bed of different types of particle, different that shape can be of different type. So having said that, so which means the dE we get as this expression, the equivalent diameter. And then what we do, we go back to this expression that del P by HE was a constant multiplied by mu u by dE square. Okay. So here now we replace all these equivalent terms, where ui, interstitial velocity, which is difficult to measure, so let's convert that to the superficial velocity, which is easier to measure, because this we directly get from the input values or the inflow rate, that is superficial velocity divided by the void space. Equivalent height is a constant term multiplied by the height of the bed, because again the equivalent height is not the straight height. In case of tube it is just h, but here it is a tortuous path through which the flow is happening. So equivalent height is a constant multiplied by the height, or the factor multiplied by the height of the bed. dE equivalent diameter or the hydraulic diameter we have just calculated in terms of SV, which is the surface area of the object per unit volume of the object. So then we replace these parameters here in this expression, and we get an expression of del P by H that contains superficial velocity, a constant term, voidage, and the SV term, which is the surface area per unit volume of the object, that is square, and K3 becomes a constant term of K1 multiplied by the K2. This is the famous Koenig-Karman equation for laminar flow through randomly packed particles, irrespective of its shape. Any kind of particle, when there is laminar flow through a stack of those particles, when there is fluid is flowing, a single phase flow is happening, okay, the pressure, the frictional pressure drop across that bed, okay, or the pressure gradient, rather here it is del P by H that is written here, is given by this expression. Okay. So now this K3 constant term depends on the particle shape and surface properties. It has been observed by several experiments, a wide range of particles, wide range of particle types having different density, different shape. It has been seen that this K3 value depends on the particle shape and surface property, and this value is numerically close to 5, a constant value of 5. Now for mono-sized sphere, mono-sized means the sphere of same size, of same diameter, let us say x, all the spheres. Okay. So in that case, if you make a packed bed of those spheres of diameter x, okay, of height h, then the del P across that packed bed will be this expression, because if we now put K3 value as 5 and SV that was there is V square is 6 by x. We get 180 multiplied by this factor mu u 1 minus epsilon square by epsilon cube divided by the x square that is already there. This is again a famous form of the Kauseni-Kármán equation for spherical object, again monosphere spherical object, laminar flow. These conditions have to be met, then you can use this expression to find out what would be the pressure gradient across a spherical mono-sized spherical object of diameter x when a fluid of viscosity mu is flowing at a superficial velocity of u and when the bed voidage is epsilon, that is known to you. If this criteria or this information you have handy, then you can use this formula to calculate this pressure gradient or the pressure drop across the bed. So this is the laminar condition. Okay, when there is a flow through the packed bed of monocyte sphere. So similarly, what could have been the pressure drop for the turbulent flow? For the turbulent flow in a randomly packed bed of monocyte sphere, the expression is this one, which is minus del p by h. Here we have 1.75 as the coefficient, rho f u square by x multiplied by 1 minus epsilon divided by the epsilon cube. This expression is named by other scientists duo, which are the Bark-Plummer equation. Like that is we mentioned as Kauseni-Kármán by two scientists, Kauseni and Kármán. Here we have Bark and Plummer. They developed this relation after several experiment, several observation, and we have this relation when there is a turbulent flow over mono-sized sphere having randomly packed the orientation and this voidage and other parameters, the fluid properties are known, then we can use this expression to calculate the pressure gradient across the bed. So is there any expression that we can use it for this whole range that covers the laminar and turbulent? Yes, that is there, and that is the Argand equation, which we will discuss in the next class. With that, I thank you for your attention and will see you in the next class. Thank you.